Hello everyone and welcome back to Math Chat with Nasir. Today we are going to explore one of the most powerful and widely used mathematical tools in science and engineering, the Fourier Transform. If you already have some knowledge of the Fourier Transform, it will help you develop a deeper understanding and gain new insights into its underlying concepts. If you are completely new to the topic, don't worry, we will begin with the fundamentals and gradually build up to more advanced ideas. Throughout this lecture, we will cover the mathematical foundations of the Fourier transform, its key properties, and its practical significance. We will also study the discrete Fourier transform and the fast Fourier transform. So let's get started. We start with the sine function. We have three sine functions denoted by f1, f2, and f3. f1 is equal to sine 2 pi x, f2 is equal to sine 6 pi x, and f3 is equal to sine 4 pi x. Let us plot these three functions on the xy plane. If we put x equals 0 in f1, we obtain f1 of 0 equal to 0 because sine 0 is 0. Next, f1 of 1 by 4 is equal to sine pi by 2, which is equal to 1. So we plot the value 1 corresponding to x equal 1 by 4. For x equal 1 by 2, f1 of 1 by 2 is equal to sine pi, which is equal to 0. For x equal 3 by 4, we have sine 3 pi by 2. The angle 3 pi by 2 is equal to 270 degrees or equivalently minus 90 degrees. Therefore, sine 3 pi by 2 is equal to minus 1. Finally, for x equal 1, we get sine 2 pi equal to 0. If we plot all these values, we obtain the graph of the function f1. It has a repeating pattern. This whole graph is called a sine wave. It repeats on the negative side as well. This single pattern repeats throughout the graph of the function. One such pattern is called a cycle. We can see that one cycle is completed at x equal 1. It takes 1 unit of time or 1 second if time is measured in seconds to complete one cycle. Likewise, if we plot the second function, we obtain a graph like this. It also repeats itself, but the repetition of the cycle is faster than that of the first function. f2 completes 3 cycles in 1 second or in 1 unit of time. Likewise, the function f3 completes 2 cycles in 1 second. The number of cycles completed per second is called the frequency of the sine wave. It is usually denoted by f. The first function completes 1 cycle per second, therefore its frequency is equal to 1. The second function has a frequency of 3, whereas the third function has a frequency of 2. There is another related concept called the time period, denoted by the capital letter T. The time period is the time it takes to complete one cycle. The higher the frequency, the lower the time period, and vice versa. Frequency and time period are inversely related. The time period of the first function is 1 second. The time period of the second function is 1 by 3 because it takes 1/3 of a second to complete one cycle. Likewise, the time period of the third function is 1/2 of a second. In fact, the time period is equal to 1 over frequency. Now suppose we multiply the sine function by a factor of 3. The shape of the graph remains the same and the frequency and the time period also remain unchanged. Only the height of the sine wave changes. The peak will now be at 3 and the trough or the lowest point will be at minus 3. Here is the general formula for a sine wave. F of t is equal to a sine 2 pi into f into t. Now we have used variable t instead of the variable x. Both are equivalent way of representing a function. Here a is the amplitude and f is the frequency. The time period can be determined from the frequency. For example, we have a function f4 of t equal to 3 sine 5 pi t. This function has an amplitude of 3 and a frequency of 2.5. It means the function completes 2.5 cycles per second, and the peak and the trough of each cycle reach 3 and minus 3 respectively. Similarly, f5 of t is equal to 2 sine 10 pi t. The amplitude of this function is 2 and the frequency is 5. And therefore, the time period is 1 by 5. Let us go a little bit further and consider two functions that are the sum of sine waves with different frequencies and amplitudes. The function f is the sum of two sine waves, where the first sine wave has an amplitude of 2 and a frequency of 1.5, and the second sine wave has an amplitude of 4 and a frequency of 3. The function g is the sum of three sine waves having respective amplitudes of 3, 4 and 2 and respective frequencies of 1, 2.5 and 4.5. Let us try to find the Fourier transform of both of these functions f and g. The Fourier transform simply identifies the amplitudes and frequencies of the sine waves whose sum is equal to the given function. Let us first consider the function f. We plot its Fourier transform. On the x-axis is the frequency and on the y-axis is the amplitude. The function f contains a sine wave with a frequency of 1.5 and an amplitude of 2. So we draw a bar at f equal 1.5 with a height of 2. The second sine wave has a frequency of 3 and an amplitude of 4. Therefore, we draw another bar at f equal 3 with a height of 4. Likewise, the Fourier transform of the function g has bars at f equal 1, f equal 2.5 and f equal 4.5 with heights equal to their corresponding amplitudes. The first graph represents the Fourier transform of the function f, and the second graph represents the Fourier transform of the function g. From the Fourier transform, we can reconstruct the original functions, and likewise we can obtain the Fourier transform from the original functions. This is the basic idea, but Fourier transform is not that simple. For the function which is explicitly the sum of the sine waves, finding the Fourier transform is straightforward. But in practice, the functions have complex descriptions. They are not explicitly written as sum of different sine waves. For example, how can we identify the sine waves whose sum is equal to the function g1? And likewise, the sine waves which add up to the function g2. So this is not always straightforward to find the Fourier transform of a function, because functions mostly are not written as sum of explicit sum of sine waves, but the sine waves are inherent in the function description. So we need to find sine waves which are inherently part of a function. In the same way, the Fourier transform is not always in the form of discrete frequencies. For example, a function has 3 sine waves and another function has 5 sine waves. Finding the original function in both cases is easy. What about when the Fourier transform itself is given as a formula over a continuous range of frequencies? How can we add up sine waves of frequencies in a continuous range? For example, let the Fourier transform be f of f equal 2f plus 3. The sine wave of frequency 1 has amplitude 5, and those of frequencies 2, 3, 4 and 5 have respective amplitudes 7, 9, 11 and 13. Just add up the sine waves multiplied by their corresponding amplitudes, but these are not sine waves of discrete frequencies. What about sine waves of frequencies 2.5, 2.7 and so on? So instead of summation, we integrate the sine waves of all frequencies. So this is the inverse Fourier transform. This means we find the original function by integrating a continuous range of frequencies multiplied by the formula of the Fourier transform. We multiply it with the sine function and integrate it over the frequencies, and we get the original function. So how can we determine the Fourier transform of any function? Given f of t, we can find the Fourier transform using this integral, and the inverse Fourier transform can be obtained from this integral. But we are not done yet. These are not the exact equations for finding Fourier transform of a generic function. Before moving forward, let us look at another concept related to sine waves. Here is the plot of a sine wave. This sine wave has a frequency of 1/4 and an amplitude of 3. Now look at another sine wave which has just been shifted about 1/4 of a cycle to the left side. It has the same frequency, the same amplitude, but slightly a shifted version of the first sine wave. We can say that the first sine wave starts from angle 0 and the second sine wave starts from the angle of 90 degrees. Otherwise, both sine waves have the same shape. The starting angle is called the phase of the sine wave. We have already seen that the first sine wave can be written as f of t equal to sine 2 pi 1/4 into t, which is equal to 2 sine pi by 2 into t, or 2 sine pi t divided by 2. How can we write the second sine wave? Since there is a shift in the angle, the second sine wave actually starts from angle 90 degrees. Therefore, the second sine wave can be written as g of t equal 3 sine pi t by 2 plus the phase pi by 2. The phase of the first sine wave is 0, whereas that of the second sine wave is pi by 2 or 90 degrees. A sine wave having frequency f, amplitude a and phase phi can be written as f of t equal a sine 2 pi ft plus phi. Now the question is, how can we find Fourier transform of a function which inherently contains sine waves with non-zero phases? In that case, our previous formula for the Fourier transform will not be useful. To incorporate phase in the Fourier transform, we use Euler formula, which is e raised to power iota theta is equal to cos theta plus iota sin theta, and e raised to power minus iota theta is equal to cos theta minus iota sin theta, where iota is under root minus 1. Instead of using sine waves as the basis for computing Fourier transform, we use e raised to power iota theta as the basis in the updated definition of the Fourier transform. E raised to power iota theta encodes frequency as well as phase in its definition, and therefore this definition of the Fourier transform is the final definition. Usually omega equal 2 pi f is used in different definitions of Fourier transform in literature. Omega is called the angular frequency. So if we put omega equal 2 pi f in the Fourier transform and the inverse Fourier transform, we get Fourier transform and inverse Fourier transform as these two formulas. Let us summarize the definitions of the Fourier transform and the inverse Fourier transform. Fourier transform is obtained by integrating from minus infinity to infinity the function f of t multiplied by e raised to power minus iota omega t. The integration is performed over t. Whereas the inverse Fourier transform is equal to the integration from minus infinity to infinity of f of omega multiplied by e raised to power iota omega t. The integration is performed over omega. Since we have substituted omega for 2 pi f, we obtain df equal d omega divided by 2 pi. Therefore, there is an extra factor of 1 by 2 pi. This is our neat and clean final definition of the Fourier transform and the inverse Fourier transform. The Fourier transform is one of the most versatile mathematical tools in engineering and science. It allows us to analyze signals in the frequency domain, making it possible to remove noise, compress data, detect patterns, reconstruct medical images, enable modern wireless communication systems such as Wi-Fi and 5G, process radar signals, and extract features for machine learning and artificial intelligence. Suppose we have 8 discrete signal values. You can think of these values as the values of the function f evaluated at 8 different times. We don't know the original form of the function, we just have these discrete values. In this case, we cannot apply the continuous form of the Fourier transform. Instead, we need to apply discrete Fourier transform. Again, we will develop discrete Fourier transform step by step. Suppose we have these 8 discrete values of the function evaluated at t equals 0 to t equals 7. Again, the concept is the same. We need to find sine waves of different frequencies whose sum is equal to these signal values. We need to consider sine waves of frequencies 1 by 8, 2 by 8 and maximum up to 7 by 8. We cannot go beyond sine wave of frequency higher than 7 by 8 because up to 8 time units we can have a sine wave of frequency up to 7 by 8. We cannot go beyond this. We also need to consider sine wave of 0 frequency which has all values equal to 1. So we have sine wave of frequency 0 which is all ones. Sine wave of frequency 1 by 8 means 8 values. It just completes one cycle up to time 8. Sine wave of frequency 2 by 8. These are again 8 values and contains 2 cycles. And finally, we have a sine wave of frequency 7 by 8. It has 8 values and completes 7 cycles. Let us generalize it. Suppose we have n discrete values of a function at time t equals 0 to t equal n minus 1. These values are represented by x0, x1, x2 and up to x minus 1. Instead of using sine waves, we use exponentials of different frequencies. To find the DFT, we need to calculate n values y0, y1, y2, yn minus 1 such that x0 is the sum of these values multiplied by corresponding value of y, x1 like this, and generally xt is the sum of the column t values multiplied by corresponding y values. These y values are called the DFT of the signal x0, x1, x2, xn minus 1. Suppose x0, x1, x2, xn minus 1 is the discrete time signal. Its discrete Fourier transform is defined as this formula. There are n different values of y as well, from y0 up to yn minus 1. The corresponding inverse DFT is defined as the summation. Here are the formal definitions of the discrete Fourier transform and the inverse discrete Fourier transform. This is the DFT and this is the IDFT. The discrete Fourier transform can also be defined as a matrix multiplication. Suppose the discrete time signal x is represented as a column vector x equal x0, x1, x2, xn minus 1 and define the matrix W as this. The dimension of the matrix W is n cross n. It has n rows and n columns. The Fourier transform Y is just the matrix multiplication W and X. The vector Y has n rows and 1 column. Likewise, the IDFT can be performed by multiplying conjugate transpose of W to Y. Let us discuss the fast Fourier transform or FFT. FFT is just a fast method to calculate DFT. Otherwise, DFT is equivalent to FFT. Just FFT is computationally faster. For n equal 10, DFT requires 100 operations. For n equal 100, DFT requires 10,000 operations to perform DFT. The computation time of DFT increases by order of n square. On the other hand, computation time of FFT increases by order of n log n, where log is taken with base 2. Let us compare the computation time step by step. For n equal 100, DFT requires 100 operations and FFT requires 33 operations. So FFT is 3 times faster. For n equal 20, FFT is 4.6 times faster. For n equal 50, 9 times faster. And for n equal 100, FFT is 15 times faster. For n equal 1000, FFT is 100 times faster. And if n is equal to 100,000, FFT computes discrete Fourier transform 6,000 times faster than the direct method of DFT. So for large values of n, which is very common in practical problems, FFT is thousands of times faster than the direct method of DFT. Let us summarize our today's lecture. Fourier transform of a continuous time function f of t is equal to the integration f of t multiplied by e raised to power minus iota omega t, where integration is performed over t from minus infinity to infinity. The inverse Fourier transform is defined the same way. There is an extra factor of 1 by 2 pi and the integration is over omega from minus infinity to infinity. Below are formulas for discrete time Fourier transform and inverse discrete Fourier transform. The matrix form of the discrete time Fourier transform and inverse discrete Fourier transform are defined as the matrix multiplications. Thank you for watching. If you like our videos, please support us by subscribing to the channel and inviting others to subscribe to the channel. Thank you.